Okay, let's start. So I think this is maybe our final recitation, so I wanted to have a final exam practice for you guys. So basically this is how it's going to run. I'm going to present a question, read it over for you guys, and try to read it through, clarify some details maybe. And then I'll give, I hope you guys brought some maybe pencil and paper to write on. I'll give you maybe 2 or 3 minutes, depending on how hard the question is, to try to solve it. And then I'll go over the solution, asking you guys, maybe some people to contribute answers, or maybe voting on which answer we think is correct for if there's a few options. So this is just kind of a collection of questions that that we covered in the class that might be kind of similar to some of the stuff that you'd get on the final exam. So hopefully it's a decent assortment of things. Okay, so let's get to our first question. Start off talking a little bit, just some probability, talking about conditional independence. So let's suppose you've got variables a, b, c, and d. And you want to show that a is independent of b and c given d. So a is conditionally independent of b and c given d. Show that this implies that a is conditionally independent of b given d. So if you guys want to start, I'll just give you a couple minutes to try to solve that one out, then we'll go through the math. Okay, so just going through the solution to this guy. So we want to show that, that a is conditionally independent of b given d, right? So basically we want to show the following. Probability of a comma b given d is equal to the probability of a given d times the probability of b given d, right? Because this is the definition of conditional independence. So how can we do that? We really want to use the hypothesis here that a is conditionally independent of b and c given d. So we can start out by writing the left-hand side here as the following. So we can take a sum over c and then do probability of a comma b comma c given d. So this is just a marginalization of the c variable. And then based on our hypothesis that a and b is independent of c given d, we can write the following as the product of two terms. So we take the sum over c, and we take the product of probability of a comma b given d and the probability of c given d. Actually, did we say a is independent of b and c? Yeah, a is independent of b and c. So, wrong way. Probability of a given d and the probability of b and c given d. Now note that probability of a given d doesn't depend on c, which we take the sum over here. So we can bring that outside the sum. So we just have probability of a given d multiplied by the sum over c of this last term. Probability of b comma c given d. Now just like we marginalize over c to get the equivalence between these two, we can now, we're marginalizing over c over this smaller joint probability. So this equals what we want, which is probability of a given d times probability of b given d. Cool. So this is how you show that, just looking at it intuitively, it's kind of useful to know this, that if one random variable is conditionally independent on, say, 2 others, then that means it's conditionally independent on either of them separately. Okay. So moving on to the next question, we're going to go into Bayes nets a little bit. Bayesian networks. Okay. So for each of the following pairs of Bayesian networks in this figure, and I've got 2 on the next page, so we'll go through these 2 first, and then when you guys are finished working on it, we'll go to the next slide. You want to determine if the 2 Bayes nets are equivalent. So namely, if they have the same set of independence and conditional independence assumptions. If you decide that the 2 Bayes nets for A, B, C, and D are equivalent, state one independence or conditional independence assumption that they both share. If you decide that they're not equivalent, state one independence or conditional independence assumption that one satisfies but not the other. So go ahead and start working on that. Anybody want more time? Or you guys mostly got these? Show of hands, more time? No? Okay. Okay, so who thinks for part A, the 2 networks are equivalent? Show of hands. Think equivalent? Seems about half the people raise their hand. Okay, who thinks that the 2 networks are not equivalent? Okay, a few people, raise your hand. Okay, for the people who think they're equivalent, can I get some explanation? Any of you guys over here?
Because A is independent to C, when B is given.
Okay, yeah. In both cases. Okay, that's good. So yeah, the answer is yes, they are equivalent. And that's pretty much right. If you condition on B, then it blocks A and C, so they're independent. And if you don't condition on anything, then all the guys are dependent on each other. Okay, what about for the second one? Who here thinks that the two networks are equivalent? Okay, nobody. Who thinks that they're not equivalent? Awesome. And somebody who thinks they're not equivalent, can you tell me why? Just shout it out or raise your hand.
Same with the first one. So A and C is independent.
You say independent given B in the first one, right?
Oh, and A and C is independent.
Yep, that's right. That's right, yeah. So the key thing here that you got to look for are these head-to-head. So when you've got A and C are both pointing to B, so when you observe B, it causes a dependency between A and C. So that's a key thing that's not shared by the first one. Okay, so let's go on to the next two. I'll give you guys another minute for these guys. That's okay. Same thing. We want to know, are these two networks equivalent? And these are a little bit harder. And if so, an example of a conditional dependency that they share, or if not, an example that one has and the other does not have. You guys think you got it? You want a little more time to think about it? Okay, let's talk about it. So who thinks for part C, who thinks these two networks are equivalent? Okay, see a few hands, nice. Who thinks that they're not equivalent? Not equivalent? Okay. The answer is that they're equivalent, actually. Does anyone have an example of, conditional independencies that they share, that they want to say? Somebody who raised their hand for equivalence?
Yeah, it's actually this is the same to the first
Sure.
example we see. So here given B,
Yep.
A is independent to C.
That's right. And that's true both in the...
Without given, if C is not given, B is independent to C.
Okay, right. If C is not given, yep, right, exactly, because you have a head-to-head on C. So that means that, that D is independent of both A and B when you don't observe C, right? So part D, who thinks that they're equivalent? Equivalent, one taker. Who thinks that they're not equivalent? Okay, looks like most people. So for people, the answer is they're not, they're not equivalent. And so for people who think they're not, does someone have a good example, maybe somebody else from over here, of what conditional dependency one has that the other one does not have? Say again? B and D independent given A. Right, in the first one. And not in the second one. That's true. You can also say, I mean, A doesn't affect things so much. You can also say conditional on nothing. That same thing holds. B is independent of D in the first one and not in the second one. But you're right, it also independent or conditional on A. Okay, nice work, guys. Let's go to the next question. So Markov blankets. Do people here remember the definition of a Markov blanket? People remember or do not remember? Okay. Well, I could say it really quickly. It basically gives the answer. I forgot if we went over it in detail in the class, but it's a terminology that's useful, but sometimes we don't explicitly call it a Markov blanket. But I'll just say it. Markov blanket are the parents, the children, and the children's other parents for a given set of nodes. So with that in mind, the first question is asking what's the Markov blanket of the set A, S of nodes? So based on my definition I just gave there, can you guys go ahead and write down the set of nodes that are in the Markov blanket of A, S? Parents, children, and other parents of the children. And if somebody has a solution, raise your hand and I'll call on you. Yeah, sure.
So I know what a Markov blanket of one node is, but
Sure.
when it's two nodes, do they have to share each of the things?
Yeah, so it's a union of all the things that for one node.
Oh, that makes sense.
Yeah.
Yeah, in that case, I have an answer.
Go ahead. Yeah.
It's just ILJ.
ILJ. So we're looking for the Markov blanket of A and S, right? So ILJ is the child of A, the child of S, and the parents of both of them. But also D would be in the Markov blanket. So it's a union, not the intersection.
Oh, right.
Yeah.
Okay.
Yeah.
And then H would also.
And H, that's right, yep. And so the key thing here that's not illustrated in this figure though is suppose we want the Markov blanket of a given node here, and it's got a child who has another parent, so we want the Markov blanket of A. It includes that guy over there, okay? Includes the other parents of the children. Cool. Okay, next part, true, false. For each of the following independence assumptions, state whether it's true or false. Oh yeah, go ahead.
So my question is, we have J and H both in the Markov blanket.
That's right.
But do we keep the connection between J and H, or forget about it?
So the Markov blanket is really a set of nodes. It's not a subset of the graph. See what I'm saying? So when someone asks for like what's the Markov blanket, they're looking for a set of nodes, not
Okay, just the node.
yeah. So you're not worried about the network structure, the edges or anything. Okay, cool. So yeah, for the following four independence assumptions, probably be pretty easy based on the last question, but state whether A, B, and C, or D are true or false. I'll give you guys 30 seconds for that one. Okay, doke. You guys think you got it? Who thinks the first one is true? Most of you. Who thinks the first one's false? A few people. First one is indeed true. So if you want to get from D to S, you'll notice that all paths actually involve a head-to-head. So if we're trying to go through A, notice that like up to I, for example, you have to go through a head-to-head through A. If you try to go through H down here over to S, you have to go through a head-to-head at H. And then if you want to go to L and then J, you have to go through a head-to-head through J. So all paths are blocked by this head-to-head. And so it's conditional on nothing. It's independent. D and S. For part B, who thinks that part B is true? Who thinks part B is false? Okay, cool. And can someone tell me why part B is false?
Because D and I are not D separated in this case, because H is affecting A,
Mm-hmm.
and since D and I are not D separated, so there is no path from D to S.
You say there is no path.
And no path in a sense, no independent from that.
Okay, so there is a path.
Yeah, path is there. I mean, what I'm trying to say,
Yeah.
they are not separated, D separated. You use them for D separation.
Yep, right. Okay, cool. Yeah. And just to be clear, so the path that you'd get from it is D to A to H, that we assume is observed because we're conditioned on it, to J to S, right? Okay, part C. Who thinks part C is true? Who thinks part C is false? Okay, cool. Could someone give me a reason, maybe from over here? Maybe a path that you can get from C to J? Anyone got one? Yeah, go ahead. Say again? C, D, A, J. Yep. A, H, J. That's right. Yeah, conditional H. Okay, nice. Part D, who thinks is true? Who thinks part D is false? Just one person? A couple people? Okay, cool. And can somebody give me a path to get from C to J? Condition on it. One of the people who raised their hands? Yep, C, D, A, I, S, J. Okay, cool. Okay, nice. Next question. I think we're moving past Bayes networks now. Okay, on to Gaussian mixtures and EM. I think this is probably the most mathy question out of the ones I'll give. So I'll give you guys some kind of time to do it. And also it's something that maybe is one of the more technical parts of the class. So I think this is a good one to kind of go through in detail and pay attention to. So Gaussian mixtures and the EM algorithm. So I'll read the question. The E step in estimating a Gaussian mixture model infers the probabilistic membership of each data point and each component Z. What we mean by that is a probability of the assignment Zj given Xi for all of your data points I and all of your components J, where I indexes the data and J indexes the components. Suppose a Gaussian mixture model has two components with a known fixed variance and an equal prior distribution. So we have a Gaussian mixture model that's uniformly weighted, 0.5 weight on each component. We've got a variance at 1 for each component and two parameters, mu1 and mu2, just the mean parameter of each component that we're trying to estimate. The observed data is just one data point, which is x1 equals 2. And the current estimates of mu1 and mu2 in the EM algorithm are mu1 equals 2 and mu2 equals 1, respectively. So compute the component memberships of this observed data point for the next E step. So compute that value up there. And a little hint, we're giving you normal densities for the standardized variable, the standard normal random variable at these values, 0, 0.5, 1, 1.5, and 2 are these guys here. So go ahead and try to work through computing this probability, and then we'll talk about it in a couple minutes. OK, I think we'll start to go through it. Even if you're not finished, I can go through it. How many people feel confident that they know how to do this problem? They have the answer? OK, maybe no one, or maybe you guys are just shy, but that's OK. Either way, we'll go through it in detail. Just want to start by giving a slight background on a few things, just to clarify some points in the class before we even go into the details of this problem. So first of all, Gaussian mixture models. Generally, what are Gaussian mixture models? They're a probability distribution where you have some sort of weighted mixture of Gaussians, right, that you draw from. So let's suppose we have a data point drawn from a mixture of Gaussians. We can write this, and let's suppose the data point is like xi, the ith data point. We can write this as a sum. Usually it's written as a sum over k components, where each component is some sort of weight sub k, the kth weight, multiplied by the kth component Gaussian, where the Gaussian has components mu of k being the mean component, and then the variance component sigma squared of k. So this is just like the usual general formulation for a Gaussian mixture model, where the weights, wk, sum to 1. Oops. OK. In this problem, we have a two-component, uniformly weighted Gaussian mixture with a fixed unit variance, right? So essentially, each of these wk's, we have two components, w1 and w2. Each of them are 0.5. We assume that sigma k isn't a parameter that we want to estimate. It's fixed at 1. And we only have parameters mu1 and mu2. And of course, this is written, xi is drawn from 0.5 multiplied by a normal with mu1, comma 1, plus 0.5 times a normal of mu2, oops, comma 1. OK. Second of all, EM algorithm. Are you guys, how comfortable do people feel with the EM algorithm? Do you guys remember it and understand it pretty well from class? Decently? Sure, yeah. So a really simple definition of the EM algorithm that you could remember now and take with you for the rest of your lives, hopefully, is it's an optimization algorithm for maximum likelihood estimation in latent variable models. So if you have a model with latent variables and parameters, and you want to do maximum likelihood, if you remember from statistics, maximum likelihood estimation of the parameters, this is an optimization algorithm for that, which iterates between two steps. An E step, where you compute the posterior distribution over your latent variables, and then an M step, where you maximize the expected value of the log likelihood of the parameters with respect, where this expectation is taken over the posterior that you computed in the E step. So you iterate between these two steps. You compute the posterior over the latent variables, and you maximize your expected value of your parameters, where the expectation is taken over that posterior in the E step, back and forth between these two. And at the end of the day, it's a greedy optimization procedure that gives you a maximum likelihood estimate for your parameters in the latent variable model. OK, so right now we're doing a component of the E step for the Gaussian mixture model. So in the E step, you basically want to compute the posterior probability of Zj given xi, where in this case, if you remember from the explanation in the class, the z's in your Gaussian mixture model are these latent variables which represent the assignment of each data point to one of the components. And so this question is asking, how do you compute the probability of an assignment zj given your data point? Note that we've got two components here, so two possible classes. So zj, actually we'll just call it zj, is in, we'll say either 1 or 2. And we've got one data point, x1, which is just equal to 2. And then we've got, from a previous step in the algorithm, we're told that mu1 is equal to 2 and that mu2 is equal to 1. This is just the current positions. Because it's an iterative algorithm where each m step we update our parameters, mu1 and mu2. So we're saying from last iteration, mu1 is equal to 2, mu2 is equal to 1. Like that, okay? We're also given this other piece of information here, this kind of hint at the bottom, which I'll write down here. So these are values of a standard normal PDF. So that's if you've got 0 mean and 1 variance, what's the PDF of a certain value at, for different x values here. So if we draw up like a table to help us remember where we've got x and then normal of x given 0, 1. We've got like 0, 0.4, 0.5, 1, 1.5, 2. And over here we've got 0.35, 0.24, 0.13, and 0.05. So does this part make sense when it's kind of written a little bit interestingly over here, a standard normal y. But does this make sense here, what the information is giving? Yeah, the PDF values at each of these x values? OK. So now what we want to compute, which I'll erase this for a second, right here. Right. Now what we want to compute is the probability of zj given our x value, which is equal to 2. So let's start. So zj, keep in mind, it could be either 1 or 2, two different classes, because this is a discrete assignment variable. So let's start off by computing the probability that zj is equal to 1, given that our xi is equal to 2. OK? We can actually drop this j subscript. This indexes like each of the observations. We only have 1, so we can say probability that like the ith assignment is equal to 1, given that the first assignment variable is equal to 1, given our first observation is equal to 2, because we only have 1 observation. So how do we compute this? The first thing we want to do is apply Bayes' law, which you guys probably remember. So just writing out Bayes' law, we can write this as the probability of x given z times the marginal probability of z divided by the marginal probability of x. Just a usual application of Bayes' law, which I'll write up now. OK, cool. Hopefully this is familiar to you guys, Bayes' law, written up like this. OK, so now what we need to do is compute each of these 3 components. So first of all, let's compute this first guy here. Can anyone give me a way to compute the probability of x1 equals 2, the observation equals 2, given z1, the component equals 1? Does anyone know how to do that? Say again? 0.4, and why do you say that?
Because the mean of the first normal distribution is 2, right?
Sure.
So here, actually, according to the table, the probability, the density should be 4, right?
OK, that's right. Yeah. So yeah, just to recap what you were saying there. This is the first value we're computing here, right? This probability we know is a normal distribution because its probability of an observation coming from one component is normal. We know that the first component, I just erased it, but mu1 equals 2, mu2 equals 1. So it's a probability that the first observation equals 2, given that the mean parameter is 2. So you can look here on our table. We're assuming that this is like a 0 mean random variable. So a normal PDF at 2, 2 is equivalent to a normal PDF of 0 at a mean parameter equals 0. So we know that this value here is 0.4. Okay. How about the probability that the component equals 1? Do we know how to compute this? That's right, yeah. So this is just the prior over both components. We know that it's a uniform mixture. So the probability of the first component is equal to the probability of the second component. That's 0.5. That's right. OK, how about this bottom one right here? So this is the marginal probability of the observation equaling 2. Can you guys think of a way to compute that? This one's a little bit trickier. Say again? You don't have to. There's another way to do it that you don't find it. But the way I'm going to do it is to find it. Yeah, that's right, yeah. So you have to marginalize. So I'll go through that. So just to, before I do the computation, just to kind of go into what you were saying about whether you have to do it or not, one strategy to carry out this problem is just to compute the numerator for the first, the first class, compute it for the second class, and realize that those two things should sum to 1. So you can therefore figure out what both probabilities are by normalizing. However, what you can also do is compute this thing exactly here, and then for the second part, you just do 1 minus whatever value we're going to get, and that also gives you an answer. So we're going to go do it that way. Plus, it gives us a chance to think about what it means to compute this marginal here. So keep in mind that this marginal here, we can write it out as the following. The sum over our components, z sub j, of the probability that x1 equals 2 comma z sub j. So essentially, we take the sum over each of these components. Sorry, the sum of the probability that x1 equals 2 given the first component times the probability of the first component plus the sum, or the probability that x1 equals 2 given the second component times the probability of the second component. So I'll write this all up. It's essentially this sum. We're just marginalizing out the latent variables here. OK, so that's what that equals, this guy here. And then we can write this out as 0.5. So each of these prior probabilities on our classes are 0.5 times. For the first class, we've got a normal distribution at 2 with parameters 2 comma 1, because this is the first component, so the mean is 2. Plus 0.5 normal of 2, x1 equals 2, given that the mean component's at 1 and the variance is again 1. Oops. So again, if you look at our table, this guy is, we're looking for a value at a normal centered at the mean. So that's this first line here. So that's 0.4. So this is 0.5 times 0.4. Plus, we've got a 0.5 times a normal density where we're querying at 2 and the mean parameter is 1. So they're 1 separated. So if we look at this table, that would be this value here, because this is the value where we're querying at 1 given a mean of 0. So it's equivalent to querying at 2 with a mean of 1. So that's 0.5 times 0.24. OK. So yeah, the denominator is a little bit more complicated, but it turns out that if you take the product 0.4 times 0.5 divided by 0.5 times 0.4 plus 0.5 times 0.24, it equals 5/8. Cool. So I don't know if that's value that some of you gotten, but hopefully that's a value that some of you got. So now if we want to do the same calculation for the probability that z1 equals 2, because we know that these probabilities should sum to 1, we can just do 1 minus 5/8 for that. So writing that out, I'll erase this real quick. Probability that z1 equals 2, given x1 equals 2, equals 1 minus the thing we've computed here, which is 5/8, which equals 3/8. Okay. So that's one way to do the problem. And keep in mind the other way where you know that these two sum to 1, so you just compute the numerator for both cases, and then you can normalize to make sure that they both sum to 1. Okay, cool. So that's probably the, oops, did my laptop fall asleep? It's probably the most math-intensive question. Usually, we're probably not going to ask you things that require too much math, just because it's not a long time for the test. Okay, next question. So this is kind of a question where you describe differences and similarities between the k-means algorithm and the Gaussian mixture model, or the EM algorithm for the Gaussian mixture model, because there's a lot of similarities between the two. And you can actually view k-means as a sort of extension of the Gaussian mixture, which this question will explain how. Okay, so a GMM and k-means are closely related. The latter is a special case of the Gaussian mixture model. The likelihood of Gaussian mixture model with z denoting the latent components can be expressed typically as marginal probability of x equals the sum over z of the probability of your observation x given z times the probability of z, where probability of x given z is the multivariate Gaussian likelihood conditioned on the mixture component, and p of z is the prior on the components. Such a likelihood formulation can also be used to describe a k-means clustering model. Which of the following statements are true? Choose all correct options if there are multiple ones. So the first option is that probability of z is uniform in k-means, but this is not necessarily true in Gaussian mixture model. Part B, the values in the covariance matrix in the likelihood probability of x given z tend towards 0 in k-means, but this is not so in a Gaussian mixture model. Part C, the values in the covariance matrix and probability of x given z tend toward infinity in k-means, but not true in Gaussian mixture model. And part D, the covariance matrix in the likelihood probability of x given z in k-means is diagonal, but this is not necessarily a case in Gaussian mixture model. So I'll give you guys a minute to think through how you feel about each of these, whether they're true or false. Okay, I'm going to stop you here because we're a little bit running short on time. For part A, who thinks part A is true? And who thinks part A is, okay, one true. Who thinks part A is false? 0. Okay, so true wins. And true is correct. So yeah, it's not necessarily the case in a Gaussian mixture model. So we had a uniformly weighted one for our last question, but I could have a Gaussian mixture model where you apply the EM algorithm, where I have the first component weighted as 0.7, the second component weighted as 0.3, for example. You can still run EM algorithm to get a maximum likelihood estimate of the parameters. Okay, part B. Anyone think this is true? Show your hands. False? True? False? Okay. Answer is true, actually. This is kind of a cool thing that's people are actually doing this type of equivalence in like a lot of modern research, which is pretty cool. Small variance asymptotics is what it's called. But it's true that if you look at the updates in k-means, in particular the assignment of the component parameters to the closest, or the assignment of the data points to the closest component in k-means, you can actually view that as equivalent to EM algorithm, where your variance on each of your components is taken to 0, so is shrunken down. So this is actually true. So part C, do you guys think this is true or false? Hands for true? Hands for false? Nice. That's good inference there. That's right. It is false because part B is true. It turns out if you had like infinitely large variances, it would kind of be like it would be equally probable every component when you're doing assignments. So it's the opposite of just the closest one is completely 100% the one you're assigned to, which is what k-means does. Okay, part D. Who thinks this is true? Who thinks this is false? Okay, the answer is that it is true. So it's a little bit of a tricky question because really in k-means we're thinking of like a 0 kind of variance. So maybe it doesn't really matter if they're diagonal, if they're isotropic or not, because everything, when you have a point, it's kind of hard. But really is, you think of it having a diagonal or isotropic covariance when you're doing k-means. So that one's true. Okay, next question. Okay, so this is a question on co-training. Suppose we're trying to use co-training where, so this is a semi-supervised, yeah, go ahead. Yep. So yeah, they would, yeah. But it's really asking like whether it is diagonal even though, you know, it can also be viewed based on part B as the values tending to 0. Is it like a circle, you know, around? Hmm? Yeah, you can kind of think of it as, here's a good intuition. So you know in the previous problem how I fixed the variance at 1? So it was kind of like thinking about what's the best setting for mean parameters when you've got normals with a fixed variance. Where we're looking at, there was a mu1 and a mu2. They both had a single like 1 variance here. And k-means, it's sort of like the behavior you'd get is if you shrunk these down to points and looked at what the EM updates would give you. And eventually, when you shrink it down to just a pure point mass on the mean, you get the k-means updates, right? So this question is asking, if you look at this in higher dimensions and look, so say we're looking at 2D Gaussians and we're looking at the covariance matrix, it kind of is like the shape of the oval of the Gaussian. Is it circular or is it like not circular? Is it an angle? Is it axis line or is it yeah, is it circular or is it not? And what this is trying to tell you is that in k-means, it's like you shrink it down to a point where you have a circular mass around your mean, if that makes sense. Yeah.
I get the idea, but I don't really see why. Do we have to do something like mathematical proof or something?
No, this question isn't looking for proof. It's just looking for like intuition between both. But yeah, you wouldn't have to give a proof for a question. In fact, this guy would just be looking for a true or false value, you know, true or false. But or like how do you know this fact? Yeah. Okay. Well, I would say the best thing to take from this is that the answers to these questions are basically all of the intuition between the similarities between k-means and Gaussian mixture model. So if we ask you any sort of question like that on the final, you can use the answers to this because you're here for that. But yeah, in order to actually, how would you understand, you know, how would you really know like all these things? You'd probably have to you know, learn it from something else like in lecture or from a paper or something. So yeah, cool. Yeah. Okay, so let's go on to co-training. What time we got? Okay, hopefully we got about 5 more minutes. Hope we can get through this question pretty fast and then maybe on to the next one. Suppose we're doing co-training. So if you guys remember, co-training is a semi-supervised algorithm. So we don't know the labels for the question marks. We know the labels. One of them are red circles. One of the labels are blue triangles. For our classifiers for co-training, we use linear classifiers, where the first one only uses x coordinates of the data points, and the second one only uses the y coordinates of the data points. So from these 4 answers here, can you choose the number of iterations that will be performed by co-training until it converges? So I'll give you guys about 20 seconds on this one, so we can go fast. Okay, I'll go through the answer real quick. So if we're talking about what is co-training, what's the basic procedure? You learn each of your classifiers on the labeled data. You perform classification on using both classifiers on the unlabeled data. You then add to the training set k instances where both classifiers agree, where you choose a value for k. And then you retrain both classifiers on the extended set of data points and you repeat the process. So in this case, our first classifier is a linear classifier using only the x coordinates. So what would this first classifier label all of the question marks as? Blue triangles, right? Because the blue triangles are, the line's going to be somewhere in between these two, and they're all the question marks are to the left. Similarly, what the classifier that only uses the y values, what will it label all of the question marks as? Right, red circles, okay. So then based on how I just described the algorithm, it only adds things to the training set if both classifiers agree. So k of the ones that agree, how many will it add to the labeled set? How many will it label? 0, right? That's right. So it won't go on to the second iteration in this question. It'll just stop. So the answer is A, or 1 iteration. Okay, next guy. So quick question on PCA. Yeah, go ahead.
We never talked about this in code, right? Like if it's a linear classifier, is it necessary that it should be consistent with our labeled examples?
Should be consistent with what?
With all our labeled examples so far?
So it's kind of like you've got labeled examples, and then when you run the classifier, it doesn't necessarily have like perfect accuracy, if that's what you're asking. It just gives you the best results. So sometimes linear classifiers, they're not necessarily perfect. So for example, do you notice there's some overlap here in the data sets or in the two classes? So the line, for example, on the x-axis it would probably misclassify some of the blue triangles and some of the red circles.
So it's not a requirement that we should have a classifier to be consistent with all the labeled examples?
No. You just pick some sort of classifier. Yeah. Okay, question on PCA. This might be our last one. Sorry, we're going a little bit over. So which of the following unit vectors expressed in coordinates x1, x2 correspond to correct directions of the first, which we'll call P, and the second, which we'll call Q, principal components via a linear PCA, so not kernelized in an interesting way, respectively for each of these two data sets. So what this is asking, like for the first data set 1, it's listing the principal components P and Q, which the direction of the vector is represented by the things in the parens here for P and Q. And then the second 2 is for the second data set. So we want to ask which of these A, B, C, D, or E is feasible. It can be more than one as principal components. So you guys have just 30 seconds to think about this, and then we'll talk it out. Okay, so let's talk about this. Intuitively, first of all, what does PCA do? Okay, we can think of it as a linear transformation of the data that takes the data to a new coordinate system such that the first coordinate, or the first principal component of this new system, explains the greatest variance of the data. And what does that really mean? It means that if we were to project the data on this first component, it would have the greatest variance out of projections. And the second principal component is orthogonal to the first. And it also explains the second greatest variance of the data, and so on and so on. So if we're just looking at the first two principal components, can someone tell me a vector that could represent the best projection that would explain the most variance of the data in this diagram here for part 2? Someone give me just a direction of an arrow here that we can draw. I see people saying diagonal like this. That's right. And similarly, wouldn't this also give us kind of the same exact thing, right? Okay, cool. So how can we represent? So I've shifted this data to be in the 0 or the center of the plane. So how can we write this vector? We can write it as 1 over square root of 2, comma 1 over square root of 2, or alternatively negative 1 over square root of 2, comma negative 1 over square root of 2, right? What would be an example of the second greatest variance in this data set, the second principal component? Other diagonal? Okay, great. So this one or this one. So similarly, so this is the first principal component. We can write the second principal component as either 1 over square root of 2, comma negative 1 over square root of 2, or the opposite, negative 1 over square root of 2, comma 1 over square root of 2. Right? So this is our first and second principal components. What about the second data set here? What principal components seem to be best in this data set? Does anyone have any ideas? Yeah, pretty much any two orthogonal vectors, yeah. It's a little bit not true because when you have not an infinite number of data points, you technically have like a polyhedron of some sort, right? So some projections are going to be slightly less, but let's suppose that it's almost a circle. It's almost any two components would be best, including zeros and ones. So in that case, part A, do we think that this would be correct? And hold true? Yeah? You think so? Yes, that's right. Part A is correct. How about part B? Can anyone spot the problem in part B?
It swaps the second one swaps the principal components.
That's right. Second one swaps principal components. So B is out. Okay, nice. Part C, do we think this is correct? Yep. Okay, great. And part D, can anyone spot the problem? Yeah, second principal component, you guys are saying, is messed up. It's pointing the wrong direction. Okay, cool. So A and C are correct. Okay, cool. I think that's all we have time for. I had a couple more questions on boosting and the little join data thing, but yeah, I don't think we have time for it. I can, so these questions are actually from things that are already posted on the midterms and finals. So I can write a little post comment to my thing where I say which midterm and final I grabbed it from, and then you guys can see it.
So those are up on
On the website already, yeah. So on the website, the final tab over says previous material, and you look at, there's midterms and finals for 601 and 701, and I grabbed some questions from there that I thought were relevant. Cool. Yeah.